Hi, my name is Jeffrey Payton. I work with Yahoo, and I do the BGP network peering, and I also write code for network analysis. The code that I'm demonstrating today is Tundra. It stands for the Ultimate NetFlow Data Real-Time Analysis. The features behind Tundra are your standard source and destination AS bandwidth analysis. This is some standard stuff that you can get from C-Flow-D. Beyond that, we have transit AS bandwidth analysis. So by combining these destination prefixes with zebra BGP information, we can tell you how much bandwidth not only terminated on an AS, but passed through it on its way to other ASs. Looking at your BGP tables, you can also make custom AS macros. For example, just with show IP BGP and grep, you'll be able to determine how many ASs are behind a given peer or transit provider, so that you can do forecasting and peer merit analysis before you even bring up the connection. Another feature is applying billing formulas for cost-benefit budget analysis. So once you know how many megabits you would have sent to this fictitious AS macro, you could also apply either 95th percentile in plus out, whichever is greater, or 90th percentile in plus out, or formulas as wild and out there as Sprint's billing formula. Another thing you can do is analyze the local servers to see how much bandwidth they are sending and receiving from the internet. So you can build back individual properties. An example of this in Yahoo's case would be to figure out how much bandwidth, let's say GeoCities and My.Yahoo is using, so that you can build back those individual properties for the bandwidth that they use. Another feature of Tundra, which I particularly like, is the symmetric network performance analysis, because you could bring up all the peers in the world, but BGP isn't necessarily going to tell you that you have increased the performance or done a better job. You could be sending all of your traffic to AS701 through a T1 just because there are fewer AS hops. It doesn't mean it's a smart thing to do. So with symmetric network performance analysis, we allow for the simultaneous testing of packet loss and latency across all of your peers or transit providers to a given destination network. We also give you the AS path hop count, so you can figure out how much of your traffic, how far it has to go to get to its intended customers, how many ASs that it passes through. We'll also give you some information on DOS attack detection. This would include things like ICMP Smurf attacks, SIM floods, whether or not a given port is being bombed, like your port 179 if people are attacking your BGP interfaces. And all of this is done in real time. We've configured it to run every 15 minutes, but your mileage may vary. Now, why should you care about Tundra? Because it gives you empirical data. Finally, you have some information that can prove that your network performance is actually increasing by adding these diverse paths. You can also show that your network reliability is increasing as your AS hop count decreases. And you can do forecasting and cost-benefit analysis to show that these new peers and new transit links that you brought up were actually a good idea. And in order to determine whether or not you should be adding new peers or transit links, you can figure out how much bandwidth will be going to a given peer before you turn it up, so you don't have to invest a lot of money building out, only to realize once you got there that it was a mistake. It also allows you to focus and order who it is that you want to peer with, so that you go after the big fish first. And if some of those folks don't want to peer with you, or the transit is a little outside of your price range, it allows you to generate a compelling business case by being able to document and give them real numbers over time showing how much bandwidth this interface would, or this connection would actually use. Why did I call it Tundra? Well, my dog's named Tundra, and I had the NetFlow data real-time analysis already worked out, and she thinks rather highly of herself and came up with the ultimate. So it was a lot easier to work out than Alpine. So how does the system work? Well, we have a router continuously exporting flows. We're using version 5 flows to standard C-Flow-D collector. I applied Dave's Caucus patch, thank you very much, Dave, for generating the raw flows off of that, and we dump the raw flows to disk. An SNMP poller will poll all of the egress interfaces off of the router every 15 minutes and calculate the averages. And then we found in the data center that does about 500 megabits of traffic inbound plus outbound. Over 15 minutes, it will generate somewhere in the neighborhood of 300 megabytes of disk space of raw flows. Bill Fumarello, another person at Yahoo, wrote a very fast C parser that will rip through that 300 megs in about 21 seconds. Combining all of the information into a summary form, because since flow data is only a sampling, you can't add up the number of bytes that an interface used and say that that's how much actually went to UUNet or that's how much actually went to Sprint. What we would do is, in the case of UUNet, we'd add up all of the byte counters for AS701 and divide it by all of the byte counters that went through the interface to give a percentage that went to AS701. Another thing that it does is take all of the destination prefixes that are /32s and convert them to /24s so that we can do the Zebra lookup for all of the all of the destination subnets and figure out how much bandwidth will go to each AS along the AS path of the route to the customer. And then finally, the flow percentages are multiplied by the SNMP stats to actually give you accurate information of how much bandwidth went to a given AS. A couple caveats associated with flow data in version 5's current form is that you don't have any previous IP address, so you're not able to figure out if you have a link to a public peering exchange, who sent you given information if, let's say, you had 30 peers on the other side of a GIGI or a FAST. Because it does have a next hop IP, however, you can figure out how much bandwidth went to all of the individual peers across a public peering connection. Tundra also allows for more accurate information by, if you have a gig trunk connected to, let's say, a 2948 that has a bunch of fast Ethernet TNIs, you're not getting the SNMP statistics off of the gig interface that has the trunking, but instead you can get the SNMP stats off of the individual fast Ethernet ports. So you can get highly accurate bandwidth analysis to each of your individual peers. Now, what kind of flow data will Tundra present? For the AS bandwidth, it'll give you the inbound and the outbound and the transit, how much bandwidth actually went through a given AS. For the port information, you can find out how much went in, came in or out to a given port. This is interesting for denial of service attacks and to make sure that things like Telnet are actually shut off. For protocols, you can also see inbound and outbound traffic, which is interesting for things like Smurf attacks, and to make sure that if you don't have DNS servers in a given location, that you're not seeing UDP information, things to that effect. And again, for servers for individual source IPs, you can group them together to document how much bandwidth individual services or properties, or however you break up your organization, how much bandwidth they're using, and assign a dollar amount to that bandwidth. And unfortunately, because of the asymmetric nature of routing, we can only get the AS path information on the outbound, not on the inbound. Sorry, SBC. And so, an example of the graph. This data is from July 6th, 7th, and 8th. This is a Friday, Saturday, Sunday after the 4th of July. No, it wasn't a weekend, it was a Wednesday. I was trying to balance between giving really real information that's compelling, but not spilling the beans on what Yahoo actually does for obvious reasons. In this graph, you can see that the blue line on top is port 80. That is web traffic for DCX data center. It makes sense that the majority of the traffic would be port 80. You see that the green line below that is port 53. Makes sense that this data center has a East Coast DNS cache. And what's nice to see, the black line is Telnet at 0, and people actually using SSH for red lines. Looking at protocol information, again, you see TCP is the majority of the bandwidth. That makes sense. The green line, again, is UDP that correlates almost exactly to the port 53 from the previous graph. And you have ICMP down there at the red line. And what's interesting about the ICMP line is that you see that at the max it did 19.4 megs that we were paying for. That would allow management or whoever is in charge of this network to determine, do I really want to take the time to figure out where all that bandwidth is coming from, or where all that ICMP is coming from, or do I want to let it ride? Because we're still paying for that, just like we are for our web traffic. It also allows you to determine how much rate limiting should I actually do, so something like a keynote doesn't make our service look bad, but we're still not wasting money on this. Now, for bandwidth out, this is one of the more interesting graphs showing you how much traffic goes to. The top line is UUNet, the next one is AT&T, and they go down the line. You can get an idea of how much traffic is actually terminating on the individual ASs. But it gets more interesting when you start talking about the transit data. Now, all outbound flows, like I said, have the destination IP address. We roll up /32s into /24s so that we have less processing to do. We'll break about 5 million flows down to about 50,000 unique subnets that we'll get over a 15-minute interval. Then we look up the Zebra path and remove all AS padding. And the nice thing about the Zebra BGP table is that it's identical to the local routers that you're pulling the flow data from. So if you have a different perspective of the internet from your East Coast, West Coast, Canadian, Asian, European, what have you, ISPs, you're going to get the stats, or you're going to get the actual route that those routers are going to use. And the other nice thing is that if you make policy changes, you can immediately see data migrate from one transit provider to another. If you were to, let's say, not peer directly with, let's pick AOL, you could watch as you move their ASs from one provider to another and actually verify that, yes, that's what you intended to do and that you got your prefix list or local pref or wait or however you chose to move that traffic correct. Now, looking at the graph of how much traffic actually went to versus through an ISP, this example is for UUNet. The bottom line, the red line, is the same red line for the previous graph. The area under that line, you have no choice but to send to AS701. There's no way around that. The black line is how much traffic actually went through UUNet. And the interesting thing here is the area between those two lines. Any customers that have their own AS that aren't on 701, you can make a reasonable guess that the majority of them would have any customer that would not be on UNet's AS, you can make a reasonable assumption that they'll have their own AS and they did that so that they can multi-home. So you have the chance of picking up those customers from somewhere else. So rather than paying the $400 or $500 per megabit that UNet wants to charge, there's a possibility for the majority of the traffic that's represented by AS701 to be picked up somewhere else. Another interesting bit of information that Tundra provides is your AS hop count information. Now here, hop 0 is obviously our network, Yahoo, and hop 1 is our peering ISP. This is for a singly home data center that doesn't leverage any peering. You'll notice that only a third of 1% goes to our peering ISP. In this case, it's Exodus, which we don't necessarily begrudge because they have other web servers and other hosting properties. They don't have eyeballs. But what becomes interesting is when you look at Exodus's directly connected peers at hop number 2, you have 15 and 12% of your traffic going to those networks. And as you move farther and farther away, the vast majority of our traffic doesn't go to Exodus peers, but peers of their peers. And you have more than twice as much traffic going to peers of peers of peers as you do to those directly connected to Exodus. I'm of the opinion, especially after trying to get this laptop working, that Murphy's Law is going to have an exponential increase in the likelihood of anything going wrong as you increase the number of AS hops you have to roll through. There's more people involved, there's more likelihood of pilot error, of gophers chewing a circuit, a router going bad. Pick your poison. The farther away I have to go and the more things that are involved, the more likely they are to break. So if I can, via peering, via buying more transit, via whatever method you prefer, move the majority of my traffic to 1, 2, at the most 3 AS hops away, then I've made substantial gains in trying to increase the reliability and overall performance of my network because I mitigate the risk of having an Exodus outage take out all of my traffic. Another interesting thing about this AS hop information is that you'll notice in the graph that I cut for time that over a 24-hour interval, you'll notice that in the middle of the night, the traffic that is 2 and 3 AS hops away dips down, and the traffic that's 4, 5, and 6 AS hops away actually surpasses it as Asia and Europe wakes up and starts pulling your traffic. So you see some interesting trends in at what time of the day, how far your traffic has to go to get to the intended customer. Now for performance analysis, there's an ongoing debate, and I know that NANOG mailing list won't shy away from it, as to whether or not we want to use ICMP or send TCP packets with a bogus SYN and ACK and time how long it takes to get the reset back. The advantages of TCP are that you're going to walk through any Cisco ACL or non-stateful ACL. I should probably throw Juniper in there too, just to be fair. You're also going to be higher in the protocol stack, so the likelihood of your being queued up is less, and you're not going to be rate limited by CAR or other ICMP rate limiting features, so you're going to get better data. downside is that you look like a denial of service attack. So it's sort of a Medikit question, and what you're comfortable with. A good socket programmer could whip up either one relatively easily. The other nice thing about the testing that we do is that it's done from your network. A lot of times you have a situation where an ISP will provide you a matrix from every gateway to every other gateway on their backbone. They'll tell you how long the round trip times are, but you may not care how long it takes to get from Atlanta to Poughkeepsie because your traffic doesn't cross that link. All of the performance analysis here is done from your routers out across their interfaces and will come back into your interfaces, not necessarily to some other ISP or some other data center, some other peering transit link that you don't care about. The method that we use for setting up this testing is route maps. The reason I prefer route maps is that I can assign a single IP per peering or transit interface, and I can guarantee consistently that all of my packets are going to go out that interface. The nice thing about that is that I don't have continuous IBGP flapping by updating a bunch of /32s, and I don't have to have /32 static routes added to my routers. And you have no third-party software logging onto your routers. Depends on your comfort level and whether or not you trust that and whether you have a problem with that. I mean, obviously, everyone's mileage would vary, but I'd rather set something up once and let it ride. The best part, though, is that you can simultaneously test through every one of your interfaces to the same target all at the same time. So if we want to go to Timbuktu.net, I don't have to roll through all 50 of my transit providers and peering links at 5-minute sampling intervals and get back sometime, 5 hours later. I can actually have symmetric data that said at the same time, how are we performing? So the next steps for Tundra. I've been promising friends since the last NANOG that I'm going to write a white paper, and I really mean it. It will get written. The other thing is that I'm looking for help on developing this. This is a hobby. It's not my job. I actually have routing and router jocking to do, which I promise you I can handle better than I can a laptop. I'm looking for others. I'm also looking for maintainers to help finish baking the code and the configuration before we release it to the internet community. We absolutely want to make this open source. This isn't something that we're looking to sell. This isn't something that I get to stand up here and say, haha, we have it and we don't. We want more and more people to use it. We want more people to develop it. We want more people to build it. My goal is for Tundra to become to BGP what MRTG is to SNMP. Everybody uses it, not necessarily because it's the best thing out there, but because the price is right and they get relatively good information from it. And the licensing is GPL, and please share with us. And if you're ever around, you have to pet my dog. So if you have any questions, I'm Jeffrey at payton.com. Since I'm already married, that email address is not likely to change anytime soon. Or if it's work-related or about Yahoo, you can reach me at jpayton@yahoo.com. So, any questions?
We've got a couple of email questions. One, doesn't CFlowD/FlowScan already give us this capability?
It doesn't give you the transit data. It's going to give you the destination AS that stuff will terminate on, but it won't combine it with the Zebra BGP information to actually tell you how much bandwidth flows through that. Beyond that, I don't know its abilities to be able to aggregate interfaces from different locations because of time I didn't delve into. If you have, let's say, 4 UUNet connections to 4 different locations, each one of those interfaces has its data stored separately, so you can combine them together. So you could aggregate how much bandwidth goes out a given data center, how much bandwidth goes out a given ISP, or just a singular ISP in a given data center. So the granularity with which you can process the data is different. Also, I don't know about FlowScan's abilities to give you billing formulas. So whether or not you're 95.5 or 90% in plus out or in or out, whichever's greater, being able to apply that to give you real numbers to know what this would cost you at the end of the day.
What level of machine or machines do you use to process your flow data and generate this output?
We have a Pentium 3 850, a little 1U box with, I think it's a 30 gig disk. And after you process the raw flow information, which if you were to generate about, let's say you would do a gig of traffic, you would be generating somewhere in the neighborhood of 2.4 gigs of data over the course of an hour if you wanted to have hourly data points. So after you process that, which would take somewhere on the order of about a minute, that data can be thrown away. What you're left with are text files that have the AS number and then how many megabits came in from that AS, went out, or went through that AS. We see on average about 7,000 unique ASs hitting our flow data. And then only that text file for each one of your interfaces is uploaded to the central Tundra server that can compile and graph all of this information. So the amount of data that you're actually moving between your data centers is relatively small, and the horsepower that you need to run this is very small. We find that the cFlow-D polar takes about 20% of the CPU, and when we run the flow aggregation, it takes 100% of the CPU, but only for about a minute, or in the example that we have here, 21 seconds on this data center.
Question. Do you compare the origin AS that the NetFlow record returns to the origin AS in Zebra, and how often are they different?
We don't compare that information. I haven't. Sorry, I can't answer that. Does anybody else have any questions? All right. Thank you for your time.